So let us proceed to our second type of analysis of heat exchanger, that is effectiveness NTU method or epsilon NTU method. NTU stands for number of transfer units. What is that formula and all those things we'll discuss it later. Okay, and the physical significance also we'll discuss it later. First we will understand what is effectiveness, and there are something very important thing, and I feel that many students have confusion in this. Okay, many students have confusion in this, and I want to clear that confusion. Okay, what is that? I will say anyways. Okay, so initially the introduction was very simple. See, effectiveness is simply represented with epsilon. It's going to be what is the actual heat transfer. Okay, what is the actual heat transfer by what is the maximum possible heat transfer. So effectiveness is the ratio of, okay, write it in the statement form. Okay, effectiveness is the ratio of actual heat transfer to that of maximum possible heat transfer. Note it down properly. Maximum possible heat transfer. There is a reason why I am stressing it. Okay, you will understand it later. Okay, fine. First of all, let us concentrate on this Q actual. How to find out this Q actual? Very simple, which we already know. Q actual is nothing but m dot mc dot into CPC into TC2 minus TC1. Okay, either I can use this formula or m h dot CPH into TH1 minus TH2. I can use this formula, any one formula as you wish, because both of them are going to give me the same answer only. Okay, now very important part, Qmax. There is very huge confusion among aspirants regarding this Qmax. See, even though if you are watching this video and if you already studied heat exchanger, you already know what I'm saying about. Okay, you might know what I'm saying about. The problem here will be how to find out this Qmax. Qmax can be determined. There is one formula, very simple formula. I can directly give you that formula and I can say that just remember this, that's it. But understanding it why, that is very important, and that is what I'm going to explain to you now. See, there are two different possibilities, okay, or two different cases where we can obtain, where we can get maximum possible heat transfer. Okay, maximum possible heat transfer means what? It can happen in two ways. A maximum possible heat transfer. Maximum possible heat transfer means what? Whatever the maximum possible heat which is rejected from hot fluid, that has to be accepted by cold fluid, right? Fine. So what are the two different cases I am saying about? The first case, okay, case 1, let us concentrate on that. In general, if you consider, let us take a counterflow heat exchanger. For understanding it easily, we will take counterflow heat exchanger, okay? Now, in general, how it is going to be? This is how it's going to be, right? This is how it's going to be. This is going to be TH1, this is going to be TH2, this is going to be TC1, this is going to be TC2. But this is an actual case. It is an actual case. Maximum possible heat transfer means what? When maximum heat transfer is possible, let me write both the cases so that what happens, we won't have. Okay, I will go with both the cases at the same time. Okay, this is TH1, TH2, TC1, TC2. Okay, yeah. So now listen to me. What are the two possibilities? The first possibility is, see, we know that hot fluid temperature is going to continuously decrease and cold fluid temperature is going to increase continuously. But what is the maximum possible drop in this hot fluid's temperature? Maximum possible drop. What could be the minimum temperature the hot fluid can reach? When hot fluid reaches minimum temperature, that is the point where maximum heat transfer has happened. Am I right? So if maximum heat transfer has happened, then the hot fluid would have reached minimum possible temperature. That is one case. The other case is, the maximum heat transfer would have happened when cold fluid has reached maximum possible temperature, maximum possible high temperature. See, we know that hot fluid is continuously decreasing. What could be the minimum possible TH it can reach? minimum possible TH it can reach was, the limiting case will be this only, right? This is the limiting case, and that is our case 1 also. Okay, so TC1 will become TH. What I meant to say, TH2. Okay, TC1 will be TH2. What I meant to say, the final temperature of hot fluid will be equal to initial temperature of cold fluid. That is the minimum possible temperature the hot fluid can reach. It can never go below TC1, and that is the limiting case. Okay, that is one case where we can get Qmax. Okay, how to find out all those things we will see later. Okay, don't worry. Okay, now coming to another case. What is another case? What is the maximum possible, what is the limiting case of this TC2? Of course, TC2 cannot go above TH1, right? TH, suppose hot fluid's temperature is 100 degrees Celsius. Cold fluid can never go above 100. In fact, it cannot reach 100 also. That is why it's an ideal condition. This Qmax is actually an ideal condition. This is also an ideal condition. TH can never reach TC1. Okay, TH2 can never reach TC1. It's an ideal condition, limiting case. So what is the ideal condition here in case of cold fluid? When cold fluid reach TH1, okay, that is the ideal condition. When cold fluid reach initial temperature of hot fluid itself. Okay, so that is going to be our limiting condition. So when TC1 becomes TH1 itself. Okay, that is those are the two ideal conditions. In this case, TC1 is equal to TH2. Okay, in this case, TC1 is equal to TH. Yeah, I'm very sorry. I just did one small mistake. It is TC2. Okay, in this case, TC2 is equal to TH1, and in this case, TC1 is equal to TH2. Yeah, that's right. Now, how to find out this Qmax? So, how to get Qmax here? See, we know for a hot fluid, okay, for a hot fluid, our formula is what? mh dot Cph into TH1 minus TH2, okay. For maximum heat transfer, this TH2 should be equal to TC1, okay. So that is our Qmax, m dot Cph into, I will do one small change here. Instead of writing it as m dot Cp, I will just use capital C, okay, capital C, H into TH1 minus TC1, okay, right. So this is actually capital CH, right? This is actually capital CC, okay. Am I right? And now, if suppose we fall under this case, okay, what is going to be my Qmax? See, if I want actual heat transfer was m dot C Cpc into TC2 minus TC1, but ideally, that is maximum possible heat transfer when I can obtain when cold fluid temperature reaches initial temperature of hot fluid, when TC2 becomes TH1. So when TC2 becomes TH1, so m dot Cpc into, here it is what? TH1 minus TC1. Now, instead of writing m dot Cp again, I'm very sorry. Let me replace it with C. Okay, Cc. Now compare both this equation. This is one case. This is one case when hot fluid reaches initial temperature of cold fluid. Okay, this is a case where cold fluid reaches initial temperature of hot fluid. Both are limiting cases. But now the confusion is, or if you just check the formula, okay, Qmax formula, here we are having CH into TH1 minus TC1, and here CC into TH1 minus TC1. And now, which formula I need to use actually, because we have one equation. Okay, I cannot use, they are not going to give you, it is under case 1, it is under case 2, they will never give you. I need to use any one of this formula. Okay, either I need to use this formula or this formula, but which formula to choose? How to decide that? That is the confusion which I am talking about. We know actually, I will say that what is that directly, okay, what we need to choose, I can say that directly, but why we need to choose? Okay, that is important. Okay. let me say clearly, actual heat transfer is the actual one. Okay, so how much the heat transfer is happening, that can be determined by any one of this formula. Maximum means what? There are two possible cases. First case is what? When hot fluid reaches initial temperature of cold fluid, that is the limiting case. Okay, that is the limiting case. That is the minimum temperature hot fluid can reach will be Tc1. Okay. Similarly, maximum temperature cold fluid can reach will be Th1. These are the two different cases. Okay, two possible cases. And by substituting that two condition, we got two conditions, right? Th2 has to be Tc1. Okay, by substituting that condition in Q actual, I'm getting Qmax from case 1. And here, what is the condition? What is the condition for Qmax? Tc2 is equal to Th1. That is the limiting case condition. By substituting that limiting case condition, I'm getting another Qmax. But the question is, out of these two, which one I need to actually use for solving this problem? Okay, don't think that they will be giving you either it is case 1 or case 2 in the problem. They won't mention. They will never mention. You need to figure out which I need to use out of the two possibilities. Which one I need to use? What is the maximum possible heat transfer? What is the maximum possible heat transfer? I need to figure out. How to figure out? I will explain this by using simple example by taking some numbers. Okay, so that you can understand it easily. Let me rub it off and then let me explain to you. Okay, so it's very simple. The final answer is very simple. But why? That is important. Let me explain to you. So now let us understand how can we decide which equation to use, whether to use CH into TH1 minus TC1 or whether to use CC into TH1 minus TC1 for Qmax, that is maximum possible heat transfer. In that equation, epsilon. Okay, see, listen, one point you need to understand very clearly. This Qmax is what? Okay, where I can write, I will write it here itself. Okay, this Qmax is nothing but maximum possible heat transfer. Okay, just keep that in mind. Why it is maximum possible heat transfer, why I am stressing this point, you will understand. First, let us come for this case. What does this case states? This case states that there will be maximum temperature drop in case of hot fluid. See, hot fluid is the temperature of hot fluid is getting dropped from 200 to 50 degrees Celsius. I am taking that as my examples. Okay, the example states that cold fluid is entering at 50 degrees Celsius. Okay, cold fluid is entering at 50 degrees Celsius and cold fluid is leaving at 120 degrees Celsius. Hot fluid is entering at 200 degrees Celsius and hot fluid is leaving at 50 degrees Celsius, which means final temperature of the hot fluid is equal to initial temperature of cold fluid, which means there was maximum drop in temperature for hot fluid. Okay, this is our first case, right? As there was maximum drop in temperature of hot fluid, there will be maximum heat transfer which is going to get rejected. Hot fluid is going to reject the heat, right? So maximum possible, okay, that is the maximum because that's the limiting case. Okay, I hope you remember this is the limiting case, right? If you want, I will show you like this. Okay, this is the actual case. This is the actual case. This is the limiting case. Okay, since in order not to confuse, I just given you the direct one. Okay. Yeah. So the maximum case, the limiting case. So maximum possible heat rejected from hot fluid. That's going to be equal to what? CH into TH1 minus TC1. In our example, I'm going to consider CH as 2. Okay. Some just for example, for making you to understand. 2 into TH1 is what? 200 and TH2 is, sorry, TC1, right? TC1 is 50. So 200 minus 50, which is 150. So that's going to be 300 kilowatt or watt, whatever. Let me take this is kilojoule. That is, this unit was in kilojoule. Okay. So it is kilowatt. Fine. Now, this is maximum possible heat rejected from hot fluid. Now coming to this case states cold fluid is entering at 50 degrees Celsius and it is leaving at 200 degrees Celsius, which is nothing but entrance of hot fluid. Okay, so I'm taking the same value. Okay, same value. This 120 degree, 80 degree is just for an example, but you need to make sure that in both this example which I taken you, the cold fluid entrance condition and the hot fluid entrance condition is not varying, which means I'm not changing this TH minus TC1 value. Okay, in this case also, cold fluid is entering as 50, but leaving is different. Okay, but hot fluid is still entering at 200 and it is leaving at TC1. Okay, and here also hot fluid is entering as 200, cold fluid is entering at 50 only, which means I am keeping TC1 condition and TH1 condition same for both the cases. Only change which we are going to get is, in first case, TH1 is reaching TC1. Okay, that is, in first case, hot fluid is reaching TC1. The second case, cold fluid is reaching TH1. That is the difference. Okay, what does it mean that cold fluid is reaching TH1 in the sense? What actually it is indicating? So what is actually it is indicating? It is indicating that this cold fluid is accepting, cold fluid is absorbing maximum heat to reach this point. Okay, so let me write that point also. Maximum possible heat, okay, absorbed by cold fluid is equal to what? Let us take CC as 5, just for an example I am taking it as 5. TH1 minus TC1, still it remains 200 minus 50 only. That's going to be 150 into 5, it's going to be 750 kilowatt. Now say, which one I need to consider it as Qmax? Do I need to take that as Qmax or do I need to take this as Qmax? Think logically. We know that effectiveness is equal to Q actual by Q maximum, right? And this Qmax is nothing but what? Maximum possible heat transfer. By considering case 1, which means by considering hot fluid is reaching cold fluid's inlet temperature, I am getting my heat transfer to be 300 kilowatt. By considering second case, by considering cold fluid is reaching initial temperature of hot fluid, I am getting 750 kilowatt. My question here was, what value I need to substitute for in this formula? Okay, in this formula we know Q actual is very simple, it's not going to change at all. But what about Qmax? Think. If you are saying that Qmax is 750 kilowatt, I hope that many of you will say, okay, I hope at least 50% of the students will say 750 and few of them won't say anything and few of them might go with 300. The correct answer was 300. Why? First, let me give you an analogy. Okay, let us consider that there is a glass or there is a bottle or something which is having 1 liter of water. Okay, which is having 1 liter of water. Okay, and let us consider there is another bottle. Okay, another bottle which is empty. Okay, another bottle which is or else let me do it in another way. So let us consider two different cases. Okay, two different cases. First case, I'm having a bottle or glass which is having 1 liter of water. Okay, it is having 1 liter of water. I need to take this, I need to pour it in this. Okay, a small glass. And let us consider the small glass capacity was only half a liter. Okay, only half a liter. Now, can I able to pour all that 1 liter inside that half a liter glass? Will I able to pour? Obviously not. See, I can able to pour some part, maybe until this, maybe some 0.2 liters or 0.3 liters or 0.4 liters. Maximum I can pour 0.5 liters only, half liter only. I cannot pour 1 liter, even though I have 1 liter water in one glass. I won't able to pour that complete 1 liter water in another glass which is having a capacity of half a liter only. I can pour 0.1, 0.2, 0.3, maximum I can pour 0.5 only. Note it down. Okay, that's the first example. Now the second example which I am giving you, analogy again. I have half a liter water. Okay, I have half a liter water bottle. It is completely filled with water. Now I want to pour this. Okay, I want to pour this in a 1 liter water bottle. Okay, I want to pour this in a 1 liter water bottle. And now my question is again, can I able to pour it fully? That is, can I able to fill this 1 liter water bottle, can I able to fill this 1 liter glass fully? If I have only half a liter of water, obviously I won't able to fill 1 liter. I can fill some 0.2 liters, maybe 0.3 liters, maybe 0.4 liters, or maximum I can fill half a liter only. That is the point I want you to understand. That is the point. That is what here also. Let us compare now. See, whatever the heat hot fluid is rejecting, that has to be accepted by, that has to be absorbed by cold fluid, because heat exchanger, there is no heat which is going to go out of the system. The interaction is going to happen only between hot and cold fluid. The heat, whatever the hot fluid is rejecting, that has to be absorbed by cold fluid. Or in other word, okay, whatever the heat, maximum possible heat the cold fluid can absorb, that is the only heat cold fluid can get from hot fluid. I hope you would have got a point. Let me compare it and say, okay, listen. In this example, we got 300 kilowatt. What is that 300 kilowatt? Maximum possible heat hot fluid can reject. Okay, hot fluid can reject 300 kilowatt. But cold fluid has the capacity to accept 750 kilowatt. But hot fluid cannot give, right? Because hot fluid has the maximum possible heat which it can reject. Which it can reject is 300 only. But cold fluid may have 750 kilowatt of capacity. It can accept it. It may have 750 kilowatt of capacity. But hot fluid cannot give. So what is the maximum possible heat exchange is going to happen? It's 300 only. It cannot go above 300 because hot fluid doesn't have that capacity. Analogy number 2. Okay, analogy number 2. Hot fluid has a capacity of 300 kilowatt. Cold fluid, that is hot fluid, it can maximum reject 300 kilowatt only. Cold fluid, it has a capacity of 750 kilowatt. But hot fluid doesn't have. Okay, hot fluid cannot reject even 1 kilowatt more than that of 300, because we can never go below this, right? We can never, that is TH2 can never go below TC1. Okay, so maximum hot fluid can reject 300 kilowatt only. Even though cold fluid can accept 750 kilowatt, hot fluid doesn't have to reject it. That is the issue. So I need to go with, compared to the two, I need to go with which one is having minimum. Same as the case there. Let us take another example. Okay, let me just give you the second example. For example, let us take CH. Okay, CH is equal to 5 and CC is equal to 2. Okay, what happens if CH is 5? Then this case I will be having 750 kilowatt, and this case I will be having 300 kilowatt. Now, in the second example, okay, I hope you are getting my point. CH5 means 5 into 150 to 750. So maximum possible heat the hot fluid can reject is 750. If CC is 2 means maximum possible heat the cold fluid can accept is 300. Now there is again a problem. What's the problem? Hot fluid can reject more heat. Hot fluid can give 750 kilowatt. But cold fluid doesn't have that capacity to accept. But we know in heat exchanger, whatever the heat the hot fluid is rejecting, that has to be absorbed by cold fluid, because we are insulating it. There is no heat which is going out. Right? We are insulating the system completely. So only within that system, only heat interaction is going to happen. So that is the second case. Now, hot fluid is having more. Okay, it can reject, maximum it can reject 750. But maximum cold fluid can accept only 300. I hope you are getting my point. So even though I have 1 liter of water, even though I have 750 kilowatt of heat, even though I have 750 kilowatt of heat in hot fluid, but I have a capacity of only half a liter, which means cold fluid can accept only 300 kilowatt, not even 1 kilowatt more than that. So what is going to be the maximum possible heat interaction? It's not 750, it is 300. Not even a single kilowatt I can transfer more than 300. Hot fluid can give 400, it can give 500, it can give maximum 750. But if cold fluid doesn't absorb, then then there is no then it's not going to happen, right? We are insulating the system fully, so only heat interaction can happen between them. So I hope you got my point, right? So what is the conclusion? The conclusion is I need to take minimum of this 2, and in both the cases, as we know, TH1 minus TC1, TH1 minus TC1 is constant, which means I need to look into the C value. Whatever the C value is minimum, that is going to be my Qmax. Okay, so finally I can give this formula like this, okay, in general. C minimum into TH1 minus TC1. So what you need to do in case of problem solving, all these explanations are fine, but what you will do in case of problem solving, you will be having CH value, you will be having CC value, right? Heat capacity for hot fluid, heat capacity for a cold fluid. If you don't have also, you can find out M into Cp. After finding out, compare them. Whichever is minimum, that you take, you substitute here, that will give me Qmax. I hope it's clear, right? Why I am taking C minimum. That is what I explained to you with the analogy, with the example, many things. And why I stressed this point this much, because when I was preparing for GATE, I had this confusion. And I didn't get a proper answer from anyone. And even I couldn't find any answer in any books. And that that question keeps on coming into me. That is, that question was haunting me. Okay, whenever I revise heat transfer, whenever I go through heat transfer topic, that question was haunting me. And finally, I found out this particular logic, which clearly explains why I need to choose minimum C value, why I need to choose minimum heat capacity value for finding maximum possible heat transfer. Why I need to choose minimum heat capacity value? Because if I choose minimum heat capacity value, if heat capacity value was minimum, then only compared to the heat transfer value will be minimum. And I given you the two cases, right? Either, even though cold fluid can accept more, hot fluid cannot give. It can give 300 only. If suppose hot fluid can give 750, it can give more, but cold fluid won't able to accept, it can accept only 300. Okay, so whatever this complete explanation, you need to remember this formula. Okay, this is the formula which you need to remember. We will proceed discussing this. So let us finally finalize the effectiveness. Okay, so we know that Q actual is equal to Cc into Tc2 minus Tc1 or Ch into Th1 minus Th2. We can use any formula for finding Q actual. Now there are two different cases which can come in question. Okay, so the first case is Cc is less than Ch. Heat capacity of cold fluid is less than heat capacity of hot fluid. What is that C? C is nothing but m dot into Cp. Okay, if Cc is less than Ch, C minimum is going to be Cc itself. Am I right? So minimum heat capacity will be Cc. So this is our basic formula. First, what I am doing, in place of Q actual, I am using this. Okay, I am using this formula. And in place of Qmax, a general formula, C min into Th1 minus Tc1. And C min is nothing but what? Cc here. So I am substituting C min as Cc, and Cc gets cancelled. Finally, this is my formula. You don't need to remember this formula because this is Tc1. Okay, you don't need to remember this formula, but just I am giving you so that it will be convenient for you. So whenever Cc is becoming minimum, use Q actual. You better use Q actual formula as this, Cc into Tc2 minus Tc1. I'm not saying that you cannot use that. You can use that formula also. You can use that formula also here. But what will happen, numerator and denominator, these two Cc's won't get cancelled. You need to substitute it and solve it. One extra step. That is why it's better if Cc is minimum, use this formula and proceed so that you will get effectiveness only in the term of temperature. Now coming to here, the same case, if Th is less than Cc, then C minimum will be Ch. Okay, so Q actual will become this formula. Okay, this will be Q actual, and C minimum is going to be Ch. So again, simply cancel this 2. Okay, so in numerator Th1 minus Th2, numerator same Th1 minus Tc1. You don't need to remember again. Just simply I am giving you that idea. Okay, if C minimum is Ch, use this formula. Okay, for Q actual. If C minimum is Cc, use this formula for Q actual, just for making the steps easier. Okay.